Hi, this is John Whitaker for the Mathematical Analysis class, and this is our 22nd video lecture, and our 21st video lecture ended with the video recording stopping before I was through with the theorem that we were working on. That had two parts, and so I want to go back to that theorem, pick up where we left off after I remind us where we left off. So there was this theorem we were looking at, and here's what it said. It had two parts. It says if E bar is the closure of a set E in a metric space X, then the diameter of the bar, the closure, will be equal to the diameter of E. And the second part of this theorem was that if case of n's is a sequence of compact sets in X such that case of n plus 1 is contained in case of n, and case of n is different from the empty set, and if the limit as n goes to infinity of the diameter of the case of n's equals to 0, then the intersection, as n runs from 1 to infinity, of case of n, contains exactly 1 point. Okay. So we left off by proving, we were in the midst of proving part A. And the way that we were doing that was we wanted to show that these two numbers were the same. And what we had proven was because E is a subset of E closure, the diameter of E must be less than or equal to the diameter of E closure. What we were also going to do, but hadn't completed yet, was to show that the diameter of E closure was less than or equal to the diameter of E. Both of those inequalities combine to give us that the diameter of E closure must be equal to the diameter of E. And we had done some work in showing that the diameter of E closure was less than the diameter of E in order to progress that way. Let me remind us what we had done. Okay, so more formally, for the proof for part A, we have shown that the diameter of E was less than or equal to the diameter of E closure. Okay, that's what we had done. Also, we had let epsilon be greater than 0. Then, for any P and Q that were in E closure, okay, we have shown that there exists points P prime and Q prime that were in E such that the distance between P and P prime was less than epsilon, and the distance between Q and Q prime was less than epsilon. So that's what we had done. Okay? And now we want to continue on. So this kind of picks up where we left off. Okay. So here, if you notice that the distance between P and Q, so these are two arbitrary points in E closure. And we look at this, well, that's going to be less than or equal to, by property of the metric, the distance between P and P prime plus the distance between P prime and Q. And then that's going to be less than or equal to the distance between P and P prime plus the distance between P prime and Q prime. So I'm working with this distance and inserting the point Q prime plus the distance between Q prime and Q. Now, this is going to be less than epsilon, plus this is going to be less than the diameter. Now, these P prime and Q prime are in E, so it's less than the diameter of E, plus epsilon. Okay? And so what we have is that the distance between P and Q will be less than, well, strictly less than 2 epsilon plus the diameter of E. And so this was a true statement for P and Q in E closure. And so that means that this number on the right is going to be a upper bound for all of the collection of all of these types of distances. And so that means that the sum of that collection, here I'll write down, that is the diameter of E closure, is going to be less than or equal to 2 times epsilon plus the diameter of E. Now, since E is an arbitrary positive number, the diameter of E closure being less than or equal to 2 times epsilon plus the diameter of E implies that the diameter of E closure must be less than or equal to the diameter of E. And I'd like to argue through why that implication is true. So I'll do that in a parenthetical argument here. So the reason that we say that this implies this inequality is because if not, so suppose not, suppose the diameter of E closure is bigger than the diameter of E, then that would say that the diameter of E closure minus the diameter of E is going to be greater than 0. Okay? So, if we multiply that by 1/4, we get 1/4 the diameter of E closure minus 1/4 the diameter of E is going to be greater than 0. This quantity here is going to act like my epsilon. Okay, so since the diameter of E closure is less than or equal to 2 times epsilon plus the diameter of E for any positive epsilon, then the diameter of E closure will be less than or equal to 2 times 1/4 the diameter of E closure minus 1/4 the diameter of E plus the diameter of E. And so the diameter of E closure would be less than or equal to, this would be 1/2, or well, I'll write it this way. Yeah, 1/2 the diameter of E closure minus 1/2 the diameter of E plus the diameter of E. And so that says the diameter of E closure is less than or equal to, well, it would be the diameter of E closure plus the diameter of E all over 2. Now, by our assumption here that we're hoping leads us to a contradiction, we're supposing that the diameter of E closure is bigger than the diameter of E. So I'll replace this by something bigger than it. So this is going to be less than the diameter of E, well, from right here. Diameter of E closure plus the diameter of E closure over 2, which equals to, well, here, if we just read here, we have the diameter of E closure is going to be less than, well, this is going to be the diameter of E closure. And that's a contradiction. So that ends the logical reasoning why the fact that the diameter of E closure being less than or equal to 2 times epsilon plus the diameter of E for any positive epsilon yields that the diameter of E closure is less than or equal to the diameter of E. So that's what we have. And so we make the conclusion for part A. What we've done is we've shown that these two numbers, the diameter of E closure and the diameter of E, are both less than, equal to each other in both directions. So they must be equal to each other. Okay, so that ends part A. Now for part B, we let K sub n be a sequence of compact sets in a metric space X, such that K sub n plus 1 is contained in K sub n. The K sub n's are always different than the empty set, and the limit, as n goes to infinity, of the diameters of the K sub n's equals to 0. Okay, what do we want to do? We want to show that the intersection as n runs from 1 to infinity of the K sub n consists of exactly one point. Okay? Okay. Now, if we let K equal to this intersection, okay, we've already shown by a previous corollary that this K is non-empty. That the intersection of compact sets that have this nesting property, if you will, case of n plus 1 is in case of n, and each one of them non-empty. That intersection will be non-empty. Now, so we know there's at least one thing in this intersection in K. But what our goal is to show that there's only one thing. So we'll argue that the K consists of more than one point then the diameter of K will be greater than 0. So if there's two distinct points in K, you take the distance between them, and that's going to be greater than 0. So the soup of all the distances between points in K will be greater than 0. Now, since case of n contains case of n plus 1, that means that the diameter of case of n plus 1 will be less than or equal to the diameter of case of n. Okay? And not only that will happen, but also that the diameter of K, it will be, because it's contained in case of n, it will be less than or equal to the diameter of case of n. Okay? That's really the most important thing. And that statement that I just made is true for every n element of J. Okay. Since the limit as n goes to infinity of the diameter of case of n equals to 0, then the diameter of K will equal to 0. And that's a contradiction. But I would like to argue why this implies that the diameter of the K will be 0. And here, the reason that this is, if this statement is true, and it is, that yields a contradiction. What it's contradicting is that we've said that the diameter of K has to be greater than 0 if it's more than 1.8. So, if the diameter of K is bigger than 0, then the diameter of case of n minus 0 will be greater than the diameter of K we have that the diameter of k sub n is going to be greater than or equal to, I guess I should say equal to, the diameter of k sub n is going to be greater than or equal to the diameter of k, and that's what this is. Okay? So, what that means is, and that's true for all n, so there does not exist an n element of the natural numbers such that for all n bigger than or equal to n, the distance between the diameter of k sub n and 0, which is that absolute value difference, will be less than the diameter of k, which is possible number, our assumption. And that would say that the limit as n goes to infinity of the diameter of k sub n is not 0, but we know it is. And so we've got that the diameter of so what this says then is, so there must be, there can only be one point. There is, and there can only be, or there is only, is what I should say. There is exactly one point. There we go. And the intersection of k sub n. And so that's the proof of part B. Okay. Next, we want to look at a theorem that's got 3 parts. Okay, here it is. Part A says, in any metric space, let's call it X, every convergent sequence is Cauchy. Don't forget, that's really the topic, the current topic has to do with Cauchy sequences. We were just talking about these diameters because they could help us talking about Cauchy sequences. Okay, part B, if X is a compact metric space, and if P sub n is a Cauchy sequence, in X, then P sub n converges to some point in X. And part C, in RK, every Cauchy sequence converges. So we got 3 kind of theorems in one here. Okay, so we want to prove this. So this is part A. We let P sub n, n running from 1 to infinity, be a convergent sequence. In X. And so what it means to converge, it means so there exists a P element of X such that P sub n converges to this P. We want to show P sub n as a sequence is a Cauchy sequence. Okay, so I'm going to use the definition of what it means to be a Cauchy sequence. So we're going to say that anytime you give me an epsilon greater than 0, so I'm going to give you an epsilon greater than 0, think of an arbitrary epsilon that's positive, then we've got to produce a natural number, we call it n, such that for all little n and m greater than or equal to this big N, the distance between P sub n and P sub m will be less than epsilon. Okay. Well, since P sub n is a sequence converges to P, there does exist an n, element of the natural number, such that let's see, what? Such that from that spot on in the sequence, the terms of the sequence distance from P, what it converges to, will be less than epsilon over 2. I'll say that. Such that for all n greater than or equal to this big N, the distance between P sub n and P will be less than epsilon over 2. Okay. So, for all m and n bigger than or equal to big N, the distance between P sub n and P sub m, by the definition of a metric, will be less than or equal to the distance between P sub n and P, plus the distance between P sub m and P. And this is less than epsilon over 2 plus epsilon over 2, which equals to epsilon. Okay. Thus, for all n and m greater than or equal to big N, the distance between P sub n and P sub m will be less than epsilon. So that says that P sub n is a Cauchy sequence. Okay, we got part B to prove next. So, if you remember, the situation for part D is we'll let X be a compact metric space and P sub n be a Cauchy sequence in X then we want to show that P sub n converges in X. That's what we want to show. Okay. So we've got to find the P for which P sub n converges. Okay, well, here's the set we're going to, or the grouping of sets that we're going to pay attention to. So we're going to let E sub big N be equal to, I call it the set consisting of P sub n sub 1, or n, I should say, P n plus 1, and so forth. So it's kind of the tail end of our sequence. And this collection of sets will be true for every n, if you will, index family of sets, for every n element of J. Now, here's a fact. The limit as n goes to infinity of the diameter of the E sub n's, that will be equal to 0. Okay, so that's a claim, and I want to prove that claim. So let's call it a claim. Now I'm going to work on the proof of this claim. So here's the proof of claim. Okay. If we let epsilon be greater than 0 be given, we're trying to prove a limit here. Okay. We need, I'm going to call it a k, it's a natural number, such that for all big N, bigger than or equal to this k, so k is the element of the natural numbers, I'm sorry, J. What we have is the diameter, the absolute value of the diameter of E sub n minus 0 will be less than epsilon. That's what we're trying to do. We're trying to find this k. Okay. So since P sub n is Cauchy, okay, there exists a k that's a natural number such that for all n and m greater than or equal to k, the diameter between P sub n and P sub m will be less than epsilon, epsilon of 2, whatever you want to say. So, let's say epsilon of 2. So, the diameter of E sub k will be less than or equal to epsilon of 2, which is less than epsilon. Since for every n bigger than or equal to k, E sub n will be contained in E sub k, then the diameter of E sub n will be less than, or equal to the diameter of E sub k. Okay. Which we know to be less than epsilon. So that says that the diameter inside absolute values of E sub n minus 0 will be less than epsilon, because this absolute value is nothing more than the diameter of E sub n. This is true for the n's bigger than or equal to j. But that shows that the limit of those diameters goes to 0. That proves the fact. Let me write that up. So, the limit as n goes to infinity of the diameter big E sub n, that equals to 0. So that ends the proof of flying. Okay. Now, since the limit as n goes to infinity of the diameter of E sub n equals to 0, then the limit as n goes to infinity of the diameter of E sub n closure has to be equal to 0, because these diameters are the same. We proved that. We ended that proof in this lecture earlier. So, as the diameter of E sub n equals to the diameter of E sub n closure. Okay. So, now, with the E sub n closures being closed sets, closed subsets of a compact metric space. Previous theorem will tell us then the E sub n closures are compact. We know that compact sets are closed, but closed subsets of a compact space, they're compact. And that's what we're using. Also, E sub n will contain E sub n plus 1. Thus, that gives us that E sub n closure will contain E sub n plus 1 closure. And let me run through why that's true. So here we know that E sub n plus 1 contains is contained in E sub n. And that implies that E sub n plus 1 is contained in E sub n closure. And we had this theorem that said if you give me a closed set, and that's what E sub n is, it contains E sub n plus 1, this other set, then that closed set will also contain the closure of this set on the left-hand side. So that was a previous theorem. Then E sub n plus 1 closure is contained in E sub n. So where we are, the previous theorem states that there exists a unique P in the intersections of these E sub n's. Closure. Okay. That was the part B of the theorem we finished today. Okay. So, look, all this work has been done just to give us a candidate for which we can try to show that P sub n converges to. Okay, so this has given us a likely candidate that P sub n, the sequence converges to. And so that's what I want to tell you is that we will show P sub n converges to this P. Okay, well, we let epsilon be greater than 0 be given. Okay. Since the limit as n goes to infinity of E sub n equals to 0, there exists an n sub naught that's an element of the natural numbers such that for all n bigger than or equal to n sub naught. Oops, I miswrote this. It's the limit as n goes to infinity of the diameter of the E sub n is equals to 0. Maybe I said it. But anyway, that's what should be there. So for all big n's bigger than this n sub naught, we have that the absolute value of the diameter of the E sub n's, okay, minus 0 will be less than epsilon. So for all big n's bigger than or equal to n sub naught, that means that the diameter of the E sub n's is less than epsilon, okay, because that's what the diameter of E sub n's is what this absolute value quantity is. Now, since P sub n is an element of E sub n, if you will, that way, then I'm sorry. Since P is an element of E sub n, then the distance between Q and P will be less than epsilon, and that's true for all Q element of E sub n. When n is bigger than or equal to this n sub naught. But that essentially gives us the convergence to P. And the reason is because these Q's just consists of elements of the sequence. So in other words, the distance between P and P sub n will be less than epsilon if n is bigger than or equal to n sub naught. And that says, and here you could change this to little n, Here's the little n, and that says the piece of n's converge to P. Right, so if you're a Cauchy sequence in compact, that you converge. And then the last part, a little bit long, so what we're going to do is we're going to stop here, and we'll finish up part C next time. Thank you very much.